So today's our talk is about RF energy harvester based wake receiver. And let me introduce. So as previous speaker mentioned, as previous speaker mentioned, the battery limited powered wireless sensing network node resulting in the limited network lifetime. So solution for it is to design energy efficient duty cycle MAC protocol, which is software level solution. So it extends lifetime through periodic sleep and active cycle. Drawback of this is it consumes power in idle listening and overhearing. Another solution is design a wake-up receiver in hardware level. So radio is completely switched off. We can wake up some node on demand. So if we assume the large number of sensors are deployed in some region, then mobile data collector moving around, then they collect information from sensor. So instead of using this idle listening, this mobile data collector wake up sensors, which are completely switched on. So here we can use energy harvester. So it harvests energy from surroundings such that the network lifetime can be extended. In designing a wake-up receiver, we have two types. One is active, which is the sensors can have energy from battery, and another one is passive. This is to derive energy from external RF wake-up signal. In also as a MAC protocol, in designing the way of waking up sensors can be classified into two. One is the range-based. All nodes in the waking up, the transmitter range can be woken up. And another one is directed waking up. So particular nodes can be woken up based on ID based. So some nodes can collect some specific information, while some other nodes collect other information. So we can wake up selectively those sensors based on I. So here our objective is to design low-cost, long-range, passive wake-up radio, which is capable of both range-based and directed wake-up. So let me compare our prototypes with some previous works. Here, here with mode and energy harvest with mode. Here RF based. Here are four existing ones. Those except this third one, these three works use active RFID based hardware. The one closest to our work is rich mode, this one, but it cannot provide the directed wake up capability. So we our design provides both range based and directed waking up capability. Here, this one is the design of rich mode, which is the closest to our design. Here, RF energy signal, RF harvesting circuit, and waking up circuit and sensor node. So to minimize the hardware, we get rid of this wake up circuit. Lesser hardware, and we make the ID-based waking up possible. So this one is our hardware. There is 7-stage RF harvesting circuit used. This one is connected to this sensor node. Sensor node is the Texas Instrument EZ430. This one is microcontroller and transceiver. So in the range-based waking up, RF signal is coming. Then this RF signal is converted to DC output. Then these signals wake up the slim mode from deep sleep. So DC output voltages, RF harvest energy, high is correspond to microcontroller high logic level, low is the microcontroller low logic level. So as long as this input RF power is greater than threshold to this RF energy harvest circuit, then you can have high to low to high this signal. So positive edge triggering is used to wake up the microcontrollers microcontrollers from sleep mode. And this one is the experiment setup. Sensor is woken up from deep sleep mode and it can be activated. Then, as the acknowledgement, it sends the trigger number to access point. So we use RF source. As the RF source, we use Agilent M93108. And this RF source, the maximum transmit power of this RF source is limited 20 milliwatt. So our experiment is limited up to 20 milliwatt transmission power range. So PowerCast 6 dBi antenna for RF energy harvest circuit and RF source is used. This one is the result, our experiment result. The x-axis shows the transmission RF power, and y-axis is wake up range. This blue line shows active wake up range, and we can have a linear fitting, or we can say at the 10 milliwatt there is a breaking point. So one linear line and two linear lines here meet at this 10 milliwatt. So over this range, let's say if we use 10 milliwatt, then over beyond this 82 centimeters, we can now wake up sensors. And maximum waking up range is 1.16 meters. So range sensitivity is we can get 4 centimeter per milliwatt. So we increase 1 milliwatt, then we can increase the 4 centimeter range range. So this one is performance identical to Richmond, the previous work in the literature, but we use less hardware. And directed wake up. So energy harvester circuit here, and here is RF signals coming, which carries a sequence of RFID, sequence of ID of sensors. Then these RF signals converted to this DC output. Then here in ID decoding, so interrupt arrives within a fixed duration, then it's interpreted as a 1. Otherwise, it is interpreted 0. So bit duration is T seconds. And as an example, wake up transmitter send ID 101 using return to 0 encoding and on-off modulation. So to wake up sensors, we always transmit 1 bit preamble, which is added to ID sequence. And this one is the timing diagrams of directed waking up here. So 1 bit here for this first 1.5 bit duration is used to this preamble. And each bit duration is transmit here 101. Then here is the interrupt, right? So since we use return to zero, 1 corresponds to high to low, 0 corresponds to 0, the low, completely low, and here 1 corresponds to also again the high to low. And as the interrupt arrives, this one edge triggered, so we can have 101 here. So once the ID is successfully decoded, it sends this success to access point. Then micro controller activates this sleep. Here, completely the sensors is put into the completely in this sleep. When interrupt arrives, then these sensors switch it active mode and it leaves the signal. Otherwise, it is put into the right sleep. And this one is our experiment, setup of experiment. Here is RF return to zero waveform generated, and it goes to RF source. And RF source send RF signal, which is preamble plus ID. Once node successfully decodes this ID and match the match of the ID, then it sends acknowledgement. Here we use access point and node, and this one is the system specification we have already introduced. And we send 5 ones as ID and transmitted 10,000 times. So bit duration is the larger bit duration we use, then accuracies increase. At this point, we can achieve 33 kbps with a 100% accuracy. Here we want to minimize now the stage capacitance. When we reduce stage capacitance, we can achieve a higher bit length. So this one is an example of a couple of examples. 36 picofarad from 36 picofarad to 9 picofarad. So this one is the minimum stage capacitance we can use. Otherwise, the accuracy is here degrading. And at this 9 picofarad, we can achieve the maximum feedback. So the smaller the stage capacitance we use, then rise time and fall time gets smaller. So as a conclusion, so we consider novel RF energy harvested circuit-based wake-up receiver, which performs both range-based and directed wake-up. And we provide experimental demonstration of wake-up using RF energy harvested circuit-based wake-up receiver. So we achieve high range sensitivity, which is 4 centimeter per milliwatt, and we show bit rate can be achieved 33 kbps of bit rate can be achieved using this hardware. So We want to now, we want to now design completely passive RF energy harvested wake up receivers. Thank you.